Hello guys, here Gabby again. Today we are going to talk about concurrency and async programming. We know that in production payments or environments, the fastest way to take down our service is not debugging in the business logic, is in bad concurrency, blocking threads, firing uncontrolled parallel calls, retrying everything blindly, and suddenly your latency explodes. Your downstreams melt and you are debugging a random incident that only happens under load. So in this video, I will show you how I think about concurrency versus parallelism, when async await actually matters, how to avoid deadlocks and thread starvation, how to propagate cancellation token, and how we could design an orchestration pipeline that runs multiple steps safely, as for example retries, idempotency, and consistency. Okay, so for example, concurrency means that multiple tasks are in progress at the same time, interleaved. It does not mean that they running simultaneously on CPU. It's perfect for input-output bound work, okay? HTTP calls, database queries, and Redis, okay? So that means multiple tasks are in progress at the same time. It does not mean that they are running simultaneously in the CPU. Okay, are multiple tasks that they are running in progress at the same time. Okay. On the other hand, parallelism means that we are executing work at the same time on multiple CPU cores. Okay, that's for CPU bound work. Heavy computation, compression, crypto, image processing, stuff that actually burns the central processing unit. Okay, so concurrency are multiple tasks that are in progress at the same time. Okay, they are not running simultaneously in the CPU. Okay, I repeat, multiple tasks that are in progress at the same time. But parallelism, it means execution at the same time on multiple cores of the CPU. Okay, one are tasks that are in progress, okay, at the same time, and the other one is execution at the same time. Task in progress and then execution at the same time with multiple CPU cores. Okay, so in microservices, most request flows are input-output bounded. Calling other services, calling external providers, hitting the SQL, hitting Redis. So that's where async await is a big deal. It prevents thread blocking, which improves throughput and tail latency under load. Okay? Async does not mean faster. It means you do not block threads while waiting for input output. Task does not mean thread. A task is just a handle to an operation that will complete later. Okay, with a status. Success, failure, or cancellation. It might complete via true async input-output without occupying a thread, or it might run in the thread pool if someone scheduled CPU work there. Okay. The worst failures come from mixing models, using .result or .wait inside ASP.NET. Other, firing parallel requests without limits, retrying without timeouts, not propagating cancellation. That's how we get deadlocks, that the deadlocks are classing when we are blocking async work. Thread starvation, that is when the thread pool gets clogged with blocked threads. And cascading failures because our service become a traffic amplifier into a slow downstream. Okay. So when when we could use async await and when we don't. Okay, we primarily use it as an input-output bound work, the async await, when we do HTTP calls to providers or other microservices, when we do database queries and commands, and when we do Redis and cache operations. Okay, I repeat, we primarily use async await for input-output bound work, not CPU bound work. Okay. It prevent I repeat, it prevents thread blocking. Okay, so going back, we do not use the async await because it's trendy. If the work that we are going to do is CPU bound related, making it async does not help. I repeat, we use the async await when we are doing input-output work like HTTP calls, queries, Redis, database, hitting the SQL, and so on. Okay? If we truly need parallelism for CPU work, we evaluate then to use controlled parallelism very carefully, because in a web service, burning the CPU per request can kill the throughput. Okay? For example, if we have payments that is a database, okay, plus a gateway, that's a classic input-output bound. Async is allowed o sea, the async allowed the server to keep handling other requests while waiting on the network and the database. So we should talk about what async await, but what is a task? Because we have the async and the await, and on the other hand, we have the task. What really is a task? And what async await does with that, okay? A task represents work that will finish later. It's a task. A task is something that it will finish later with success, with error, or cancellation. It's not a thread. A task is just that. It's a work that will result that will finish later, okay? In .NET, the use of task with async await gave us a standard model to write async code without callbacks, keeping code readable and sequential. So the use of task and async await in .NET provide us to a standard so we can do sequential code unreadable without callbacks. I repeat that. The use of task and async await give us in .NET a standard model where the code is readable, maintainable, but most important, we do not have callbacks and is sequential. Okay, and I repeat, a task is something, is a work that is going to be finished later, not now. It's not a thread. A task is not a thread. Okay. Does the async await run in one thread? Not necessarily. In ASP.NET Core, the key is await releases the thread while waiting for the input output. Okay? Await releases the thread while waiting for the input output. When the input output completes, the continuation resumes on any available thread pool thread. That's why I think it improves scalability, because we are not burning threads just to sit and wait. I repeat, the async await not necessarily runs in one thread. The await releases the thread while it's waiting. Okay, it releases the thread while it's waiting. When the input output resumes, the operation continues on any available thread. Okay, we are working in a thread, and we release the thread, waiting for the input output, and then the work continues with the most available thread in the thread pool. Okay, so how could we avoid deadlocks, thread starvation, and handling cancellation token? With deadlocks, we can avoid it by following one rule. We use it the async all the way, in all the project, in all the solution. Okay, no result, no wait, ever. The classic deadlock happens when we are blocking, when we block waiting for a task, and the continuation needs to resume in a context that we just blocked. Okay, ASP.NET Core does not have the same synchronization context problem as the old ASP.NET, but blocking is still causing serious throughput issues and can still create nasty contention patterns. So don't do it. How about thread starvation? The thread starvation happens when we block the thread pool threads under load. If enough requests block, the thread pool can't keep up. The queue grows, latency skyrockets, and the service randomly timeouts. How we avoid it? Using no result or wait. We using async end-to-end, explicit HTTP timeouts, and limit the concurrency when needed so we do not saturate the downstream. Okay, so the cancellation token, as you already know, we propagate it through the initial endpoint down to everything. Okay, to entity framework core, to HTTP calls, to any operation that supports cancellation. This is important because if the client disconnect, we stop wasting resources, and during a redeploy or a pod shutdown, we do full shutdown. In-flight operations can instead be cancelled instead of hanging. Okay, so how we do or use an orchestration or pipeline, for example? In an application layer, we could do explicit ordering, error handling strategy, state management, idempotency guarantees, retry policies for transient failures. It's pragmatic but not over-engineered. Okay. The key part is that we could have n groups, async aside each group, with synchronous ordering between groups. Okay, and so on. So the key takeaway here is that we use async await for input-output bound work because it prevents thread blocking and improves scalability. We do not have to confuse it with parallelism. Parallelism is CPU bound work to do simultaneously work execution at the same time with multiple CPU cores. Okay? Then a task is not a thread. A task is something, is work that will be finished later. Bien, we avoid to use result and wait, and we use async all the way to prevent deadlocks and thread starvation, and we propagate cancellation token. Okay, So I hope this helped you clarify something about concurrency and parallelism and the use cases in .NET architecture with .NET Core. So thank you and see you next time.